Hi, this video is to help you understand how to use molecular models in order to study isomers. The first thing to familiarize yourself with is the traditional colors that are used for the different elements. Shown here is a short summary of the common colors that come up that are used most often. Occasionally, colors may be substituted if we don't have enough balls of one type, as long as you keep in mind what element you're building. All of the balls have a certain number of holes drilled in them. A lot of the balls you'll find only have 4 holes, and those are for atoms that strictly obey the octet rule, like carbon, nitrogen, and oxygen. Hydrogen only has 1 hole in it because it only forms 1 bond, because there's no such thing as a 1p orbital. Other elements have more holes if they can violate the octet rule, like for instance, phosphorus often can form 5 bonds, and this is the ball that we would use to build phosphorus if it had 5 bonds in it. It has 5 holes in it. Some metal ions can form up to 6 bonds when they violate the octet rule, so this gray piece could be used for a lot of different metals that would form 6 bonds when they make complexes. The second thing you have to familiarize yourself with in your kit are the various pieces that are used to represent electrons. Electrons sometimes can exist as single bonds, as we see here in ammonia. Ammonia has 3 single bonds to hydrogens, a nitrogen and 3 hydrogens. Molecules also sometimes have groups of electrons that are 4 total electrons that we call a double bond. And double bonds are shown here in O2, and double bonds are built using these longer flexible pieces. There are also molecules that have triple bonds, a group of 6 electrons that exist between an atom. And an example of that is CO. And in CO, the triple bonds are built with the same pieces as the double bonds. So double bonds are built with these pieces and triple bonds also, and single bonds are always built with these pieces. When you draw a Lewis structure, there are often also electrons that are not in bonds. We call those non-bonding or lone pair electrons. Lone pair electrons are represented by these flap pieces. These flap are meant to be reminiscent of orbitals because the electrons are actually in orbitals. And whenever you have a lone pair in a Lewis structure, you would place one of these in one of the holes of the atoms. Isomers are different compounds that have the same chemical formulas. And the way that they have the same chemical formula but are different compounds has to do with the way that the atoms are connected. The simplest way that atoms can be connected that causes 2 different compounds to exist is if the order of the atoms is different. So this is an example of what's called the structural isomer. This molecule is known as cyanic acid, and this is an isomer of it known as isocyanic acid. If we compare both of them at a glance, we can see they both have all of the same atoms. They all have 1 nitrogen, 1 oxygen, 1 carbon, and 1 hydrogen. But if you look closely, you'll notice that the hydrogen is connected to the oxygen in cyanic acid, but in isocyanic acid, it's connected to the nitrogen. So these are different, just like beads on a string that are put in a different order are different. That's the simplest way that a structural isomer can exist. Here I show another example of structural isomers. These are both isomers, we would say, of butane. This one is referred to as normal or N-butane, and this is referred to as isobutane. If we count carefully, they both have 4 carbons and 10 hydrogens. N-butane has them, we would say, arranged in a straight chain. Even though they are not straight when we build the model, they are in a direct sequence of 1 carbon directly connected to the next. In isobutane, the longest sequence of carbons we can find is 3 in a row. So this is a 3-carbon chain which has one of the carbons branching off in the middle. These are another example of structural isomers. Another type of isomerism that's more subtle than structural isomerism is known as stereoisomerism. And I have examples here of 2 molecules that are stereoisomers of each other. Stereoisomers are different not in the order that the atoms are connected, but in terms of the 3-dimensional arrangement of the atoms in space. So if I examine both of these molecules, I could go from atom to atom, and I would find in both of them, they have 4 carbons connected in a row. 1, 2, 3, 4. Pick this one up. 1, 2, 3, 4. If I were to compare the atoms attached at each position, at the first position in both of them, there are 3 hydrogens attached. At the second position, there's 1 hydrogen. Then in both of them, there is a double bond and a single hydrogen. And finally, both of them ends with a carbon that has 3 hydrogens. So the set of connections is the same in terms of what is connected to what. As beads on a string, these are the same, but they take on different 3-dimensional shapes. The double bond causes a molecule to become rigid. So this molecule is locked in this position with the angle that you see that looks like a zigzag. This is known as the trans isomer. This molecule, on the other hand, has the double bond locked in this position where both of these carbons on the end are on the same side of the double bond. This is known as the cis isomer. And these are, in fact, different substances. You can purify this. You can have this in a bottle, and you can have this in another bottle, and they have different physical properties. They have different melting points. A lot of things about them are different. They are, in fact, different substances. They're just very subtle isomers of each other. They are, we say, stereoisomers. Now, the most subtle type of enantiomerism is very similar to the difference between the left and right hands that you have. You know that your left and right hands bear a great resemblance to each other. They both have all of the same parts. They both have a thumb and a pinky and everyone in between. But you also know that a right hand won't fit into a left hand glove and vice versa. They are actually different in their 3-dimensional arrangement. So a very special type of stereoisomerism is associated with things that are like your left and right hand. Your left and right hand, if you hold them out, are mirror images of each other. If this hand looks in the mirror, so to speak, and looks over, it would see what looks like this hand. They could be looking at each other in the mirror. If we make molecules that look like mirror images of each other, sometimes we will find that they are actually unique molecules like left and right hand. In this case, I've built 2 molecules as mirror images. And in order to check if they're the same molecule, what we would need to do is pick them up and try to imagine superimposing them upon each other. So right now, the hydrogens are pointing downward, and I'm going to imagine moving them in through space and overlapping them on top of one another. If I were to overlap them, what I would see is I can line up the hydrogens in the same direction, and I can line up one other atom, like in this case, the bromines are lined up. But if you look closely, the purple and green atoms, the iodine and chlorines, are not lined up. They're reversed. And there is, in fact, no way to take these 2 molecules by twisting them around or holding them any way that will make them superimposable. So they are mirror images of each other, and they are not superimposable. They therefore are like enantiomers. They are just like right and left hand gloves or objects that are handed like that. Now, not every molecule that you build a mirror image of has an enantiomer. Sometimes the molecule that is looking back in the mirror is actually the same molecule, and it can be superimposed. If you want to check whether or not a molecule has an enantiomer, in other words, whether it has a handedness like right or left-handed, one way to check is by examining the molecule by itself. If the molecule itself has no way that it can be divided into 2 equal halves, then we say that it lacks a mirror plane of symmetry, or it's asymmetric. And that means when it is looking in the mirror, it is actually seeing a different molecule. It means it has a handedness. So this molecule, for instance, no matter which direction I imagine slicing it, I could try to slice in this direction, and on one side I would have purple, on one side I would have green, and the other side I would have brown. I could rotate it into a different position, and if I try to slice it here, again, I have different colors on different sides. There is, in fact, no way to turn this molecule around, whether you hold it upside down or this way or turn it to the right or left, where you can find a way that would slice the molecule into 2 equivalent halves. two halves that would each look like the mirror image of each other. So this molecule, we say, is asymmetric because it lacks a mirror plane of symmetry. And that means when this molecule looks in the mirror, it is looking at a different molecule. This molecule has a handedness. Another simple rule about predicting whether or not something has an enantiomer is if it happens to be a carbon with 4 bonds on it, then if all 4 of those bonds are to unique things, then without checking for a mirror plane of symmetry, you can be sure that the molecule has an enantiomer. Here are a number of different molecules, and we can look at these molecules and look for mirror planes of symmetry to determine if they have enantiomers or not. This molecule, I could see a mirror plane of symmetry dividing in this direction. If I were to slice in this direction, half of the molecule would be the same as the half that would be on the other side. So this molecule, therefore, if I were to build its mirror image, would be the same as the molecule in the mirror. In other words, this molecule does not have a handedness, right or left. There is only one molecule that looks like this model. This has a different arrangement of those same group of atoms, and this molecule also has a mirror plane of symmetry. You might not see it at first if you tried to go in different directions, like this is not a mirror plane of symmetry because the different colors on different sides. But if you hold the molecule this way, you can see that slicing along this direction in this plane, the molecule would be cut into 2 equivalent halves. The red, blue, white balls would all be sliced exactly in half. And therefore, this molecule also does not have an enantiomer. When you're looking at this molecule in the mirror, the same thing is in the mirror as the molecule that you're holding in your hand. This molecule has more atoms attached, and that does present the possibility for enantiomerism to maybe arise. And in fact, there is no way that you can hold this molecule where you can find a mirror plane. If I try to slice in this direction, while I slice the purple and in half, and these bonds and these hydrogens get sliced in half, on one hand I have the blue, on the other hand I have the red. If I try to turn it in this direction to slice the blue and the red in half, I find that I have a purple, a phosphorus on one side, and a hydrogen on the other side. In fact, there is no mirror plane that exists within this molecule. So that means when we build the model of this molecule that is the mirror image, we will find it's not superimposable. This molecule has a handedness, like a right or a left-handed glove. Now, this is an isomer of that. This has the same collection of atoms, but the way the atoms is arranged here, we find, in fact, there is a mirror plane. If we hold the molecule like this, we could slice exactly down the middle here. We would slice in half the blue nitrogen atom, the purple phosphorus, the red oxygen, and the hydrogen. And on both sides, we would have these hydrogens. Therefore, this molecule possesses a plane of symmetry. It is not asymmetric. So even though this molecule has the same collection of atoms as the last one, this molecule, when it looks in the mirror, is looking at itself. There is no enantiomer. This molecule is not or right left-handed. There is only one molecule that we're looking at here. There isn't a left-handed or a right-handed version of it. Enantiomerism is very important in chemistry. Many natural biomolecules are enantiomeric. Natural sugars, most amino acids, and a lot of other important biomolecules have a left or a right-handedness. When a drug is purified in the United States, it has to be purified so that if there is an enantiomer, only the enantiomer that has been studied and found to be an effective drug is in the drug that's given to the person. Even though the enantiomer is a very similar molecule, it can have very different reactivity in our body because many of the molecules in our body are right or left-handed themselves.